I'm a condensed matter physicist, and in condensed matter physics, main research subject is that understanding of matter consisting of many quantum particles. Many quantum particles. For example, one of the most, familiar example is solids surrounding us. As you know, solids are consisting of many atoms, and solids includes a tremendous number of electrons. And a variety of properties of solids are determined by the microscopic property of electrons. For example, electrons and there are a lot of electrons in the solids like this. And for example, one of such a property is, I will pick up two properties of such a macroscopic property of solids. And this is macroscopic property of solids, and this is microscopic point of view at micro. One typical example is resistivity, electrical resistivity, as you know. In such a situation, we consider some electrical circuits, and there is a solid here, and by applying electrical voltage, the current flows like this, and the resistivity of this material is denoted by R. And this property is determined by the flow. Such kind of flow, electric current I is determined is a macroscopic flow of electrons. And because electrons have a charge Q equal minus E, flow of electron leads to the flow, electrical flow, macroscopic electrical flow like this. And this resistivity R determines that kinds of materials. For example, if L takes very, very large value, large R, then the material is determined as insulator. If R takes very, very small, not so large value, then the material is regarded as metal. And if the resistivity gets vanishing value, then the material is regarded as superconductor. And such kind of behavior, such kind of behavior is determined by the macroscopic properties of electrons. And another macroscopic property resulting from electron is magnetism. Magnetism. In such a situation, yeah, magnet, like for example, ferromagnet results from the electron spin of electrons. In quantum mechanics, it is well known that electron has quantum degrees of freedom, so-called spin. And this, roughly speaking, this electron has two spin states, spin up state and spin down states, and these two states are regarded as a small magnet with this ring like this position and this position. And magnetism, the origin of magnetism is understood as let's say alignment of electric spin like this. Yeah, in this way, the properties of electrons like electric charge and electric spin leads to the macroscopic property of solids like electrical resistivity or magnetism like this. And in these two topics, the experimental techniques and theoretical methods are well established. So we have a very, humankind understands these two phenomena very well. On the other hand, there are more challenging problems. For example, one of our typical example is the current of spin. Here I will explain current of spin. In the case of electric current, electric charge flows like this. Such kind of currents are regarded as a flow of spin up and spin down particle in the same direction. On the other hand, current of spin is the flow of magnetic moment, and such kind of flow is generated if spin up and spin down electron flows in the opposite direction like this. Okay, and this kind of spin current has attracted much attention because such kind of current, the energy consumption of such kind of current is much more lower than the usual electric current with Joule heating. So this kind of phenomena is important topic for engine and for device fabrication. However, in solid state materials, the creation and observation of such kind of this spin current is much more complicated with as compared with the electric current. So today this is a case of solid state material. Today I'd like to talk about this kind of spin current is well accessible if we study the cold atomic gases. This is today's my take-home message. Well, cold atoms. Idea. Study spin current. Next, I will explain why such kind of physical system is, what is this kind of physical system and why this physical system are ideal to study such spin dynamics. Cold atoms. The cold atoms are synthetic atomic gas created in the vacuum chamber, and this synthetic atomic gas. And such kind of atomic gas are confined by using magnetic field and optical magnetic field and laser beams. For example, in this case, atoms are trapped in a box trap made by laser beams, and such a gas is called atoms because typical temperature is very low. Typical from nanokelvin and microkelvin scale to nanokelvin scale. Also, by using the by using the understanding of interaction between atoms and lights, and we can widely control this kind of atomic gases. Also, and I'm sorry, and yeah, and why this atomic gas is ideal to study many body physics is that there are 2 points. The first one is this gas is very simple. And the other reason is that this gas is highly controllable. Matter. For example, one can create atomic gas consisting of only one atomic species. So this gas is very pure. For example, we can create a gas of lithium-6 atoms. On the other hand, in the solid state material, the existence of impurities are usually inevitable. So this is a quite different point compared with the solid state material. The second reason, high controllability, comes from the laser and magnetic field techniques and magnetic field techniques. For example, I will explain some examples of tunable properties of the system. For example, one can control the shape of systems. In this figure, we show the three-dimensional box system. But we can also create a lattice system by applying a counter-propagating laser beams. By using counter-propagating laser beam like this and this direction, we can create standing waves like this. And the atmosphere this lights periodic potential. So if the energy scale of atoms are very smaller than the depth of this laser, atoms are trapped at the minima of the potential. So such kind of periodic system are realized. Lattice systems are realized. Another case is that, for example, we can create more complex structure. For example, there are two large atomic gases in left and right. And if and there is a narrow channel around here, and if we and this channel, how to say, the tunnel, this channel is also controlled whether it is open or closed by using lasers like this or like this. Okay. Also, the last example is that the tunability of let's say controllability of spins. If you studied quantum mechanics, you know that each atoms have internal structure called hyperfine state, hyperfine structure. And atoms have several energy levels under finite magnetic field, and like this. And the response, if we apply laser beams, each atoms in different level, for example, this level and this level, shows different responses. So by using the different laser beams, we can by using laser beams very well, we can independently control the atoms in these energy levels and atoms in these energy levels. And also in cold atom situation, we can, let's say, control the atomic, the levels of atoms in the trap. So for example, if we, so if we choose these two states as an internal state of this gas, and we call this state as spin up, and this state, the lower state spin down, then yeah, we can create a two-component system which mimic the, let's say, fermionic systems like electrons in solids. Yes, this is the controllability of cold atoms, and by using this and this controllability, we can study. One can study create new kind of setups of spin transport, the physics of spin current. I will explain my work on this direction. Here we consider this kind of construction. And kind of construction.
It's more than 15 minutes you
I'm sorry.
Talk, so yeah.
Yeah, sorry. I will hurry up. And in this case, we consider a spin polarized gas with different spin polarization. The left is spin polarized in this direction, and the right is spin polarized in this this direction. And when as the initial state, we consider we pin this channel. So in this case, there are two independent gases here, and by remove this pin, then there are spin imbalance. So spin up, many spin up in the right reservoir, and this wants to go to this left hand side. On the other hand, spin down wants to go to this side, because there are many down here, but there are few downs here. So spin current flows in this direction here. Sorry, this direction. Yes, and we study that this kind of current is very useful to study physics of superconductor or superfluids for fermions. Yeah, sorry, I used many times, for a long time. Yeah.
Okay, so that's conclude your
Yes,
talk.
yes, I will.
Okay, thank you
conclude.
very much,
I'm sorry.
Sekino-san, for very intriguing subject. I think there are a lot of questions. So, questions? So maybe I ask first that the fact actually you draw the connection between two reservoirs. So what it looks like reservoir, it's in actual situation, it's just simply a space, or you have some conductor or anything between them.
Sorry, in this case?
Yeah, in this case.
Yeah. This kind of transport setup is quite different from the, how to say, conventional one. This conventional one. Yeah. In the introductive part, I write this kind of circuit, electrical circuit. But in this case, how to say, the sample we are interested in is here, and also we have how to say other components to, for example, to induce electrical voltage difference. But in the case of cold atoms are usually a closed system. So we cannot prepare, how to say, this kind of component. But in such a situation, we can simulate some kind of transport physics. And in this case, we consider, how to say, one kind of relaxation of magnetization. Yes, but as you know, the relaxation of magnetization. In the initial state, the left is left and down are spin polarized in the opposite direction, but in afterwards, down and up reacts to the situation without polarization. And such kind of, how to say, flow are regarded as a spin current.
Okay, thank you.
Is it?
Okay, so yeah, if Chinkai, you have a question?
Yes, thanks for a nice talk. So I just wondering, so this spin current just like a pulse, it's not like steady current. So how do you measure the current?
How do you measure the current?
Spin current.
Yeah, okay. In the case of cold atoms, we can, how to say, measure the number of atoms by using, how to say, absorption imaging. Absorption imaging is that, say, by applying laser beams, atoms absorb the light as photons, and then, how to say, by using this, how to say, so photons are, how to say, absorbed, so we can image the number of atoms.
Okay. Okay, and so what you mean you can measure the charge, but you can know at what time the current.
Yes. We can measure the number of atoms in the, for example, we can measure the number of atoms.
Oh, I see.
In sorry, maybe this one.
Also, it can distinguish the spins.
Yes, because these two states are different.
I see.
Yeah, hyperfine states. So the response to the rays are quite different, usually different. Yes. So this is down. And the spin current, here we define the spin current as for example, like this. And this is proportional to the magnetization. magnetization of left.
I see.
Yes. Sorry, I couldn't explain these points. Yeah.
Thank you.
Thank you for your very good question.
Okay. Any other question? Question from the common room?
So can I?
Yes.
Thank you.
How to create this channel? I still don't understand this channel. How to create this channel?
How to create this channel? Okay. In this case, this is a little bit how to say technical points, but in this case, we use some repulsive laser beams. Repulsive laser beams are how to say. It's I'm sorry, I'm poor at painting, so but yeah, we can how to say introduce a repulsive potential around here and here by using how to say squeezed lasers. So atoms feels very repulsive potential around here. So the shape of atomic gas becomes like this. And if we let's say apply such kind of repulsive potential like this, we can close this channel. But if we replace the potential around here, this let's say pin is picked up. So this channel is created.
Okay.
Is it okay?
Okay. Is there any further questions? If not, let's thank Sekino-san again for his interesting talk. Thank you very much.
Thank you very much.
Okay, so that's for today's 15 minutes talk. You can talk to each other over Zoom or among the common rooms now. Thank you very much. Sekino-san, you can stop the sharing screen now.